just simple because we know the universal gas constant, divide by its molecular weight. So we'll get characteristic gas constants of different gases. And this also we have seen in the last class. So total mass is equal to molecular weight into number of moles, because molecular weight is the number of kgs per mole. If the number of moles are n, so the total mass is m equal to mn. So the total volume V is equal to m into specific volume, and so PV is equal to mRT. And similarly, PV is equal to n RUT. Okay, so we can use in any form based on what variables are given. And similarly, this small v bar is molar volume. So if you divide both sides by n, so V by n is V bar. That is meter cube per mole. And so at two different states, P1 by T1 equal to P2 V2 by T2. And we know that any gas behaves like an ideal gas when the pressures are very low and temperatures are very high. Means actually the molecules must be as away from each other as possible. That is, the molecular attractive forces must be negligible, and the volume occupied by the molecules must be negligible compared to the whole volume. These two are the basic assumptions, means the density must be very low. Then all gases behave like ideal gases. And in the last class, we talked about semi-perfect gas and perfect gas. These are special cases for ideal gas. So if it is ideal gas and also Cp and Cv are functions of temperature, we call it as semi-perfect gas. And if they are constant, we call it as perfect gas. And here we have seen specific volume, internal energy, and the specific enthalpy. These are per kg, per unit mass. And if you express them per unit mole, we give a bar on the symbol. V bar, U bar, H bar means meter cube per kilomole, kj, kilojoules per kilomole, like that. So this is in mole base, on mole basis, this is on mass basis. So last class, this also we have discussed whether water vapor is an ideal gas. So when the pressures are very low, that is less than 0.1%, less than 10 kilopascals, then I can consider water vapor as ideal gas with less than 0.1% error. But at high pressures, I cannot assume that, and there will be difficulty and the errors will be very large. So in air conditioning problems, the water vapor in the air can be treated as an ideal gas, but in steam power plant applications, because the pressures, operating pressures are very high, we have to, we cannot use ideal gas relations. Okay, this also we have seen in the last class, as these are the low pressure lines and these are high pressure lines as you go up. And in the low pressure lines, if you see in the superheated region, the error is very less if you use the ideal gas relations. But as you come towards the high pressure side, the error gradually increases, and you cannot use in this portion where the errors are too high. Okay. So here you can see 56% or 152% here, 49% like that. The percentage errors are very high. And so for real gases, we define a parameter called compressibility factor, which accounts for the deviation of real gases from ideal gas behavior at a given temperature and pressure. So we define the compressibility factor Z is equal to PV by RT. So for ideal gas, it is 1 because PV equal to RT for ideal gas. So Z is equal to 1 for ideal gas. And for real gases, it can be anything. It can be greater than 1, less than 1. Equal to 1 means it becomes ideal gas. So as it is towards 1, real gas behaves like ideal gas. And so this compressibility factor is nothing but specific volume actual by specific volume ideal. And we know that V ideal is RT by P, and that is equal to 1 for ideal gases. And the farther away that is from unity, the more the gas deviates from ideal gas behavior. Gases behave as an ideal gas at low densities, this we've seen. And what is the criteria for low pressure and high temperature? The pressure or temperature of a gas is high or low relative to its critical temperature or pressure. So how can you say sometimes if you say high pressure or low pressure, with respect to what, with reference to what? So then only we can understand. I got more marks means more means how much. So maybe compare it to your previous semester or compare it to your neighbor or somebody. There should be some reference point with which you can use those adjectives high or low. Okay, so this is with related to the critical conditions. Okay. And real gas, as P tends to 0, it behaves like ideal gas, means at low pressures. And we define what is called as reduced properties. Reduced properties are the ratios of pressure, temperature, and specific volume with respect to the critical conditions. So P reduced pressure is equal to P by critical pressure. Reduced temperature is T by critical temperature. And reduced specific volume is actual specific volume by RTR by PR. So this is nothing but VCR. Okay, this is the way we get it. And if you draw a graph with reduced pressure on the x-axis and Z on the y-axis with different values of TR. So we get the curves like this. And you can see these symbols, crosses for methane and circles for ethylene, filled triangles for ethane, like that. For different gases, these curves are drawn and all of them collapse into a single curve. Okay, at TR is equal to 1.0, for all the gases, I get this distribution. That is the advantage of defining the reduced pressure, temperature, and specific volume. If I draw the curve with respect to reduced conditions, for all gases, these graphs are true. I will not have separate graphs for separate gases. So usually if I take only pressure and temperature, pressure on the x-axis and temperature as the variable parameter, so I will get graphs, different sets of graphs for different gases. For each gas, I will have a separate set of graphs. So I cannot keep so many graphs and I have to check which graph is to be used for my particular problem. So instead of that, if I take these non-dimensional reduced conditions of pressure, temperature, and specific volume, so I get all graphs collapse to a single graph. So this is a universal graph. So this is a compressibility factor chart. So these charts show the conditions for which Z is equal to 1 and the gas behaves as an ideal gas. So you can see under what conditions Z is near to 1. So if you see here, Z is equal to 1 here. So at very low reduced pressures, Z is 1. And also if TR, if you see, as TR increase, the lines go towards 1. Okay, so those things you can observe here. At very low pressure, PR is far less than 1. The gases behave as an ideal gas regardless of temperature, whatever be the temperature. And at high temperatures, when reduced temperature is greater than 2, ideal gas behavior can be assumed with good accuracy, except at reduced pressure very greater than 1. So if you can see here, again, so as TR is equal to 2, almost all places, it is very near to 1. Okay. The deviation of gas from ideal gas behavior is greatest in the vicinity of the critical point. So critical point means T equal to 1, TR equal to 1 and PR equal to 1. So TR equal to 1 is this. So you can see when TR equal to 1, the deviation, that is, it is quite away from 1. That is, that Z is equal to quite away from 1. So the deviation from ideal gas is very, very high. I should never use under these conditions the ideal gas equations. So when PR is small, we must make sure that the state is not in the compressed liquid region for the given temperature. A compressed liquid state is certainly not an ideal gas state. Okay, so there is no point in talking about compressed liquid region here because PR is small. For that, I cannot say compressible liquid act like an ideal gas. Okay, so it is to be, we have to be careful about that. So here, as you go away from this curve, it will have ideal gas behavior. and very near to that, a little bit of ideal gas behavior. But near the critical point, it's completely non-ideal gas behavior. We have seen that, right? As pressure increase, as I go up here towards the critical point, pressure increase very much. And that's why it is non-ideal gas. Similarly, if I go away from this, I will guess temperature increase very much, and so it behaves like an ideal gas. So gases deviate from the ideal gas behavior nearby the critical point. So even compressibility factor can also be determined from the knowledge of PR and VR. I need not have PR, VR also is okay because they are two are known, the other one will be known. Okay, so there are some other equations of state. There are many people who have given equations of state like Van der Waal, Berthollet, Bradley-Quang, Beatty-Bridgman, Benedict-Webb-Rubin, Strobridge, virial coefficients, right? These are various equations of state are available. But only thing is, because you cannot have a single equation of state which is valid for whole ranges of pressure and temperature and density. And we have each equation has its range of application. So we will see that. So the ideal gas equation of state is very simple, but its range of applicability is limited. It is desirable to have equations of state that represent the PVT behavior of substances accurately over a larger region with no limitations. So the more the range of application, the more better is the equation. Such equations are naturally more complicated. Several equations have been proposed. So one popular one, very popular one, usually we limit our subject thermodynamics, even advanced thermodynamics also, up to Van der Waals equation of state. The other equations of state, if you do research, we use them. Okay, Van der Waals equation of state, it is modified. It is P plus A by V square into V minus D is equal to RT. So instead of PV equal to RT, P is added with some A by V square and the specific volume is subtracted with D, and we modify the equation like this. So Van der Waals has done that. So it is called as Van der Waals equation of state. And where A and B are defined in terms of critical conditions and characteristic gas constant like this. So A is correction for intermolecular forces, because when pressure is high or temperature is low, all the molecules will be close to each other. There will be intermolecular forces due to which I will have additional pressure. So that is to be added here. So this is the effect of intermolecular forces. Similarly, as I told, the specific volume, because some of the volume is occupied by the molecules itself. When they are close, the space occupied by the volumes or the molecules also is a bit of considerable thing. So this small b represents the volume occupied by the molecules. So this is called co-volume. Okay, this is the way it is modified. This model includes two effects that are not considered in the ideal gas model. One is intermolecular attraction forces, and the other one is the volume occupied by the molecules themselves. The accuracy of the Van der Waals equation of state is often inadequate. Okay, so this is also okay up to some range of pressures and temperatures. They are okay, but the range is somewhat narrow. And critical isotherm of a pure substance has an inflection point at the critical state. Okay, anyhow, on a PV diagram, if I take isothermal lines, so if I take at a temperature here like this, so it comes down this way, horizontal, and comes down. And again, still higher temperature, it comes down like this and comes like this, like this. So as it goes up, at the critical point, it will be a single line like this. Okay, this is called as critical isotherm, and this is point of inflection where the slope changes its sign. Okay, this is called as inflection point. And there are the other equations like Beatty-Bridgman's equation of state. And okay, these are complicated. We don't discuss much about it, but we have to know about the equations. If at all, if you are given a problem in the exam, you will be supplied with the equation. So the constants are This is the ARE. Okay. The constants are 5. 5 constants are here and are given in table. Later I will show the table for various substances. It is known to be reasonably accurate for densities up to about 0.8 critical density. Okay, so this is one equation which has 5 unknowns, 5 constants, which are defined for each substance. We will see later the tabular form. There is another one, Benedict-Webb-Rubin equation of state. So you can see it is still more complicated. There are some 8 constants are there here. And these constants are 8 and are tabulated in table 3.4. And this equation can handle substances at densities up to about 2.5 critical density. So previous one, it is up to 0.8 critical density. This is 2.5. That's what I am telling. The more the equation is complex, the larger will be the range of application. In 1962, Strobridge further extended this equation, that is Benedict-Webb-Rubin equation, by raising the number of constants to 16. And this is suitable for computer calculations. Normally, it cannot be used for hand calculations. The other things can be used for hand calculations. So you can see these tabular forms. So constants that appear in the Beatty-Bridgman and the Benedict-Webb-Rubin equation of state. These are the constants A naught, small a, B naught, small b, c. For different gases, it is given like that. And P is in kilopascals, V bar is in meter cube per kilomole, T is in Kelvin. Universal constant is like this. The 8 constants of the Benedict-Webb-Rubin equation are as follows. Okay, like that they are tabulated. And there is another equation called virial equation of state. So this is an infinite series. The coefficients A of t, B of t, C of t, and so on, they are functions of temperature alone and are called virial coefficients. These coefficients can be determined experimentally or theoretically from the statistical mechanics. Obviously, as the pressure approaches 0, all the virial coefficients will vanish and the equation will reduce to the ideal gas equation of state. You can see, so as the pressure approaches 0, all these, because specific volume increases very much, and all these things will become 0, and we will get P is equal to RT by V or PV equal to RT. So the PVT behavior of a substance can be represented accurately with the virial equation of state over a wider range by including sufficient number of terms. So how many terms you use here, based on that, its range of application increase. The more number of terms, the larger is the range of application. Okay, naturally, the calculations will be more. The equations of state discussed here are applicable for the gas phase of the substances only, not for liquid or liquid vapor mixtures. So complex equations represent PVT behavior of substances reasonably well and are very suitable for digital computer applications. For hand calculations, however, it is suggested that the reader use the property tables or the simpler equations of state for convenience. This is particularly true for specific volume calculations since all the earlier equations are implicit in V and require a trial and error approach. So what happens is, suppose if you see here, so V also is here. So this is what is called as implicit equation. If I want to calculate V, V is to be calculated from V itself. So that is what is called as simply implicit relation. I cannot directly calculate. So when at that time, what I have to do is I have to do trial and error approach, assume some specific volume, substitute there, calculate the updated specific volume and iterate it, and then you can find what is the final specific volume. Okay, the accuracy of the van der Waals, Beatty-Bridgman, and the Benedict-Webb-Rubin equations of state are illustrated in figure 3.57. It is apparent from this figure that the Benedict-Webb-Rubin equation of state is usually most accurate. Out of these 3 equations, this equation is better. So you can see comparison, van der Waals equation, 2 constants and accurate over a limited range. And Beatty-Bridgman equation, 5 constants and accurate for rho less than or equal to 0.8 critical density. And Benedict-Webb-Rubin equation, it has 8 constants and it is accurate for less than or equal to 2.5 critical density. And Strobridge, 16 constants, more suitable for computer calculations. And virial may vary. The accuracy depends on the number of terms used. Okay, and okay, this equation, it shows the errors using the van der Waals equation, Beatty-Bridgman equation, Benedict-Weber-Rubin equation in different regions. What are the errors? You can see here. Okay, so if you observe, we can see that Benedict-Weber-Rubin equation will have less error compared to other two. Okay, so the order these three are given here. If you see everywhere, the lower one will have less value. 3.7, 0.1, 0.4, 2.9, 0.3. Sorry, Beatty original. Okay, so that is that actually. So we have seen in this chapter, the chapter is completed. We will see the problems later. So pure substance, phases of pure substance, phase change process of pure substance, property diagrams for phase change processes, property tables, and ideal gas equation of state, compressibility factor, and other equations of state. So these things we have discussed. And now we will see actually how we can solve the problems. We take some, because now I cannot use the board and write something. We will see from the textbook itself. Okay, this saturated water, actually I have noted the saturated tables. They are in page number 938. This is temperature based. So you can see here the temperature based saturation tables. Temperature. Okay, this is. Because these are British units, I think we'll go up. Yeah. So 888 page number. So we have saturated water temperature table. Temperature in the first column, pressure, saturated pressure, corresponding saturated pressure in kilopascals. Then we have VF, VG, UF, UG, UFG, HFG, HFG, SFSG, SFG. And so this is temperatures varying up to 373.95. And then we go for the pressure tables, pressure-based tables. This is from 890 page number. And this is up to 22,064 kilopascals. And then we have superheated tables. This is appendix table A6. And you can see here for different pressures, P equal to 0.01, 0.05, 0.1 megapascal, 0.2 megapascal, like that. I have variation of temperature. Corresponding to this pressure and temperature, I have V, U, H, and S given. Okay. So this is in page number 892. And if you go down, these are also preheated tables. And then we have compressed liquid water tables also. So this is in page number 896. So you can see here, here also for a given pressure here, I have various temperatures given here, and the U, the VU, HS are given. Okay. So these are the tables which are needed for water or steam as a working substance. And this is for ice water, we don't use it. And the next tables will be given for a refrigerant, okay, R134A. So this is also sometimes we get in the problems, or there can be many other refrigerants also. For this particular one, R134A, again, saturated tables, temperature based. It is in page number 899. Pressure based 902. Superheated 903. These are sufficient. Okay. So we'll see problems. So this is in third chapter. Okay, we will see some of the problems. So an 80-liter vessel contains 4 kg of refrigerant 134A. R134A is used here at a pressure of 160 kilopascals. Determine the temperature, the quality, the enthalpy of the refrigerant, and the volume occupied by the vapor phase. This is page number 127. Okay, so the total volume of the vessel is given, the mass is given. So volume by mass, specific volume is known. And we know the pressure here. Pressure and specific volume are known. Okay, so we have to know at least two properties which are independent to each other. Okay, so that's what we have to know. So P and V are there. And so first of all, I have to know the state of the substance, whether it is compressible liquid or saturated or superheated. So we know that as we increase the pressure, the specific volume increases continuously. So I have to check, okay? So the state of the saturated liquid water vapor mixture. At this point, we do not know whether the refrigerant is compressible liquid, superheated, or saturated. This can be determined by the comparing suitable property of the saturated liquid and saturated vapor values. From the information given, we can determine V is this. And at 160 kilopascals, if you go to saturated tables of R134A, you can find out VF and VZ. So you have to see your specific volume is less than VF or between VF and VZ or greater than VZ. So if specific volume is less than VF, that is compressible liquid. And if it is between VF and VZ, it is water vapor mixture. If it is greater than VZ, then it is superheated. So now you can check that this 0.02 comes in between these two, means it is liquid vapor mixture. So once you understand that, first thing is I have to calculate the dryness fraction. So once you get the dryness fraction, you can calculate enthalpy and entropy. And how to get it? Because V is equal to Vf plus XVFG. That formula you have to remember. V is equal to Vf plus X into Vfg, or V is equal to 1 minus X into Vf plus XVG. So these two relations we have derived in the previous class. We have seen it, how we got it. Okay, so that equation I have to use to find out the dryness fraction. You can see that X is equal to V minus Vf by Vfg, or V is equal to Vf plus XVfg. Because I know V, I know Vf, and I know Vz, I can calculate what is the dryness fraction. Once I get the dryness fraction, so I can calculate the same things, similar relations will be there for enthalpy also, because H is equal to Hf plus X into Hfg. So again, you can see from the tables, what is the value of Hf and Hfg. See, Hf is 31.18, Hfg is 209.96, and H is equal to this. I can find out the enthalpy. Similarly, the saturation temperature for that pressure, 160 kilopascals, the saturation pressure also can be obtained. Okay, so you can just look at those tables. So here at 160 kilopascals, I have to check. Okay, so R134A, the table is in 899 or 902. 902. So this is the R134A table, pressure table, and the pressure is 160 kilopascals. So at 160 kilopascals, this VF, VZ, HF, HG values are taken from here. These values are substituted there. And the saturation temperature also is given here, corresponding to 160 kilopascals. So that is the way we have to do that problem. And one more thing is asked is, what is the volume occupied by the vapor phase? So we know that X is equal to mg by m total, mass of vapor by mass total mass. So mg is equal to x into m total. So 0.157 x is already calculated. R is the total mass. So this part of the total mass 4 kgs is the mass of water vapor. Because 0.157, it is a very small value. So vapor is less and liquid is more. Okay. And the total volume occupied by the vapor phase is V is equal to mg into Vz. Okay, Vz is already known. Mg is calculated here. I can calculate the total volume occupied by the gas or vapor. Any doubt in this problem? Is it okay? Okay, we will see some more problems. Thank you. So superheated vapor. So 1 pound mass of water fills 2. Okay, this is feet cube British units. I will not see that. So determine the temperature of water at a state of pressure 0.5 megapascal. H is 2890 kilojoule per kg. Okay, this is one thing, right? So the temperature is, we have to find out the temperature. Pressure and enthalpy are given. Two properties are to be given. Okay, so first I have to know again whether it is compressible liquid or saturated or superheated. So for that, again, I have to go for saturated tables, find out what is the HF and HG for this, and you see what is the value of H, whether it is below HF or between HF and HG or above HG. So again, I will go to the saturated water tables. This is pressure-based 0.5 megapascals. Okay, so here the page number is 890. This is pressure-based tables, and what is the, I forgot. So the pressure is 0.5 megapascal, means 500 kilopascals. Okay, 500 kilopascals. I have to see HF and HG. HF and HG are here, and 500 kilopascals, 640 and 2100. 640 and 2100. So it is given, sorry, this is 2890. Yeah. So 640 and 2100 we have seen. So Hg is less than this. So H is more than Hg. That's why it is superheated. So I have to go to superheated tables. And in the superheated tables, again, I have to see 0.5 megapascal. So superheated tables, it is in 892. So that is 0.5 megapascal. 0.5 megapascal is here. Okay, and some 2890 or something is there. So I have to see where the 2890. So it is between these two values. I didn't remember that value. So I have to see in between which two values it lies. So I have to find out those two and I have to interpolate. So we will see that how that interpolation is done. So here at 200 degrees centigrade it is 2855.8. At 250 it is 2961. So this is 2890. So I have to interpolate. How to interpolate? I have to calculate temperature, which is to be calculated to be taken as y, and which are available is taken to be h, the x. So y minus y1 is equal to y2 minus y1 by x2 minus x1 into x minus x1. So this is y1, y2, this is x1, x2. I can calculate slope of the line. So y minus y1 is equal to m into x minus x1. M is y2 minus y1 by x2 minus x1. And y minus y1. Y1 is, okay, this is, okay, y1 is the y1 is this and the x1 is this 2890. So I can calculate what is the value of y, that is unknown value of temperature. So using that straight line equation, I have to find out this. Okay. And compressed liquid, usually we don't get this type of problems, but okay, anyhow, we will see. Determine the internal energy of compressed liquid water, 80 degrees centigrade and 5 megapascal, using data from the compressed liquid table and saturated liquid data. What is the error involved in the second case? Okay, the exact and approximate values of the internal energy of liquid water to be determined. Okay, at 80 degrees centigrade, saturation pressure of water is 47.416 kilopascals, and since our pressure 5 megapascal is greater than P saturated, naturally it is compressed. Okay, so that is compressed liquid. So how can you find out this P sat? You have to go to saturated tables, see what is the saturation pressure for corresponding to this particular temperature. So that you can find out from the tables as 47.416 kilopascals. And we know that you compare these two pressures. So because this pressure is very high, 5 megapascal, it is obviously compressed liquid. Then go to compressed liquid table, which we have seen already. So for 5 megapascal, you go to the 5 megapascal table and temperature is 80 degrees centigrade. I can find out what is the internal energy. Okay, this is directly seeing the values from the compressed liquid tables. For approximation, many times some tables, books may not have compressible liquid tables. So then I have to calculate from saturation table. So from the saturation table, we read U equal to U at 80 degrees centigrade, that given temperature, you find out what is UF. Okay, this is the value. Okay, this itself directly you can use. You can see that this error is very less. Okay, because during compression, this internal energy will not change much at the same temperature. Okay, so you can see that the error involved in these two is only 0.34%. Okay, this is the way we can do. And okay, this is a problem which involves all the tables. Determine the missing properties and the phase description in the following table. So at every state, you have to know at least two values. Okay, so here pressure and dryness fraction are given. Here temperature and internal energy are given. And here pressure and internal energy are given. Here temperature and pressure, and this and this are given. Okay, if pressure and dryness fraction is given, it is obviously a liquid vapor mixture. So I can use, you get from the pressure tables at 200 kilopascals, you take down VF, VG, HF, HG, SF, SG. Then you have formula V is equal to, V of the mixture is equal to VF plus XVFG. H is equal to HF plus XHFG. S is equal to SF plus XSFG. And X is known, and VF, VG and all things are known from the table. So you can find out enthalpy and entropy, everything. Okay, then coming to the second one, temperature is given and U is given. So at this temperature, Again, you see whether it is saturated or superheated like that. If it is superheated, then you have to again interpolate for the required pressure. Okay, and if it is saturated, then U is equal to UF plus XFG. At this temperature, you find out UFUZ, and you can calculate first dryness fraction. And once the dryness fraction is known, you can calculate the enthalpy and all. So in that way, so if you are given both temperature and pressure, it is obviously naturally either compressed liquid or superheated. It is not saturated. So that you can find out. Again, from the pressure tables, and if the dryness fraction is given, and at this pressure, you find out VF, VG, UF, UZ, and V is equal to VF plus X VFG. Like that, you can calculate this. So the procedure is given here, everything. Okay, this is the way you have to do the problems. So you go through the the exercise problems, and also from the other books also. There are many problems that have been solved. You can go through it. You have to be familiar with the tables, how to get the data, how to use it. Every time you remember, right, there should be two properties minimum. Either one of the temperature and pressure must be known, and in the remainings, either U, H, S, X. Out of these two, one should be known. If U or H is known, V, U or H are known, you have to first calculate the dryness fraction. Then you can calculate the other properties. If X is given straight, you can calculate the specific volume, enthalpy, entropy from the table values VF, VG, UF, UZ like that. Okay, this is the way you have to solve the problems of fused substance. Any doubts? Okay, today I didn't have time to collect any information of any story. Okay, one story I will tell you. Okay, a nice story. So there is one person who is interested, a small boy, he is interested in observing the nature. And because maybe he's a future scientist, all scientists, the main basic attitude or the quality of a scientist is loving the nature, observing the nature, and learning from the nature. Okay, this fellow, he found a cocoon, and he asked his parents, what is this? And actually, this is a cocoon where the caterpillar becomes a butterfly through this phase of cocoon. And this fellow gets surprised. How this caterpillar is so horrible to look at, and how it becomes so beautiful butterfly, and how this cocoon changes it. Just really, I want to observe it. So he has taken that small plant into his room, and he started observing it. So he went on observing, because the real scientists have to have a lot of perseverance and patience. Okay, he observed, and that's after some point of time, he started seeing a small crack in it, and he is thrilled, right? He wanted to see now it's coming out like that. So he started observing it, and slowly that crack increased like that, and he is so enthusiastic. But after some time, it stopped. That crack stopped growing. He didn't understand what happened, and is it not having sufficient strength to come out? Is it not possible for it to break it open and coming out? Maybe it's very weak. So he was very much worried. So he wanted to help that poor creature. So what he has done is he has taken a small scissor, and he used the scissor to increase the crack size. Like a little bit he cut, and then later that creature has opened the crack, and it has fallen down. It has a little bit of swollen body, and no wings, and the wings are not coming out, and it could not fly. It is just limping there. He's worried, and he thought maybe he heard from his parents that there will be premature babies who will who took birth before the completion of the 10 months, and they will take a lot of time to grow and become normal. So he thought maybe it is premature, and he started observing whether it can become better. but unfortunately it was limping, and it could never fly. And he really felt sorry. And then he asked his science teacher, what happened, why it is not flying, and like that. I like it very much. I love it like that. And the teacher told, so unfortunately, my friend, with your love of it, so you have overtaken the nature's laws. So what happened is, so when it is trying to come out through that small crack, that swollen body gets pressed while coming out. When it is getting pressed, the fluids inside that body goes into the thin wings of the butterfly and it gets life into that. So because you have obstructed or constrained that particular process, what happened is the fluids didn't go into the wings and it didn't get the life into the wings. And throughout its life, it has to limp like that. So this is actually the story happened. But okay, what is the moral of it? So means in our life, we may face so many problems, and all problems are designed for us by the nature. And through problems only and adversities only, man becomes strong and beautiful. The more problems you face, the more you become strong. You can see the people also who are confident and all are the people who struggled a lot in the earlier life. The more you struggle in your earlier life, you more confident and strong in the latter life. So everything is designed by God. So what exactly said is, whenever you face adversities, instead of complaining and cursing, you just praise the God or praise the nature because they are planned for you. You welcome the adversities. It is planned for you to make yourself beautiful and strong. Okay, so this is the story I wanted to share with you. Okay, anything else? So my 1 hour is over. And tomorrow we don't have class, but we have the test at 5 o'clock, right? You will get the link at 5 o'clock. It is 1 hour duration, right? And it is first 3 chapters, I told Prajna. So the first 3 lectures, right? First 3 lectures, whatever I have told. And okay, there are totally, I think, 70 questions are there, out of which 5 small numericals are there, very, very small. You need not use even calculator. So each of the problems are of 2 marks. So totally 75 marks it is. And uh, you have to submit before 6 o'clock, right? It should not be even 1 minute later. So otherwise I won't get that. It will not accept it. So try to log out or submit at least 1 minute before, 1 or 2 minutes before that. Okay. So it will not take much. Don't think there are 60 bits or 70 bits and sorry, giving 60 minutes. Actually, if it is a written exam in the campus, I give 100 bits for 20 minutes and they are filling the blanks and people submit it even sometimes before the time they submit it. And now it is only multiple choice. There is nothing to fill and everything is whatever I told you. Yeah, it is a Google form. Okay, I will send the link. Okay, 5 o'clock you will get the link and 6 o'clock you have to submit. Okay. Okay, thank you very much. We'll meet again in the next class. Okay. All the best. Thank you. Thank you. Thank you to all.